Hello, welcome to our webinar this afternoon, Developing an Effective Vibration Program. My name's Chris Eyman. I work for Acoem USA. We're going to talk today about walk-around, portable, wireless, and online monitoring using vibration analysis. I'd like to introduce myself first. I'm a professional mechanical engineer licensed in the state of Louisiana. I went to LSU. I'm an ISO Cat 3 vibration analyst, an asset reliability practitioner, and have experience working in paper, oil and gas, petrochem, steel, raw materials, you name it. I live in Louisiana and we have just about everything up and down the river that you can imagine. We're going to start off with why vibration and why is it important, especially when we're talking about reliability and asset protection. The first thing is, just bluntly, machines fail. Machines fail for a variety of reasons. They wear out due to improper design, shipping, premature deaths, installation defects, improper support structures, use, and lack of maintenance or general neglect. Some machines fail rapidly. Some machines take a while to progress and fail. Some, when they fail catastrophically. Others slowly fade into the limelight. The failures impact the bottom line and can have impacts to the environment. Some take a long time to fix and are very expensive. Some can quickly be repaired and replaced with no impact to the process or the bottom line. Point is, there's a mix in your facility, but over time, all machines will fail. Vibration data we can use to show machine health. And the whole point is to predict and act on failures so that they are not catastrophic and minimize the downtime of the machine and the plant. You have 4 major areas for these failures. They can be mechanical, electrical, structural, or process related. All of these failures can be identified and preemptively acted upon using vibration analysis. The main faults that we see using vibration are lubrication/bearing defects, misalignment, and unbalance. We can identify other faults, but these are the primary faults that we identify and are able to act upon. All of these faults also have preemptive things that we can do to stop them before they get worse and cause catastrophic failure. Today we're going to talk about some general vibration program goals, what those are, and some more detail about how to act on those goals. Number 1, we need to identify condition changes. We need to determine a cause for those changes, create an action plan, correct those changes, and then document and share our findings. Documentation is going to be key to all of this because we need to support our findings and prove that we were successful with our program. Who do we need to achieve these goals? Everyone in the facility needs to be involved. It's a top-down culture of maintenance and reliability that needs to trust our practices, trust our plan, and implement the process. The plant management needs to buy in that these early detection faults are detected. Maintenance needs to make the corrections. Operations needs to trust when we tell them a machine is failing that it's failed. And production needs to know how to plan for those failures so that they can meet their goals. Who we have shapes the goals that we are trying to achieve. So the availability of personnel to conduct the vibration analysis and analyze the data, the experience of that personnel. Do you have anyone on staff that's a vibe analyst? Coordination with operations and production so that they know how to plan these failures and the maintenance actions, and the time to collect, evaluate, and report and act on the data that we are able to achieve. What machines will be included in the program is also very important to the success of the program. We need to look at criticality, accessibility, how easy is it to get to them and collect data, how complex are they, what is the environment around them, are the personnel even allowed to get near that piece of equipment, is there a safety issue, is the location far away and hard to access, maybe at a remote pumping station, what is the process conditions that this piece of equipment acts in, what is the failure mode? And what's our ROI? Because without a return on investment, is the vibration program even important? So we need to show all of these things to make a successful program matter. Number 1, we need to determine criticality. Criticality shows us what we need to do and how we need to analyze this equipment. So something with a high criticality, because it has 100% stop to production or pose a safety risk or environmental risk, needs to be monitored much more closely than something that has a low criticality, because there's a full online spare, meaning no stop to production. It doesn't have a cause for safety risk or release, and is very inexpensive to replace. So we're going to use different technologies to analyze and monitor the high criticality versus the low criticality. To determine criticality, we need to know our machine. So we need to go through our equipment list and document speeds, bearing information, possible failure modes, how it operates, how many spares do we have in line or in the warehouse, what is the environmental risk, what is the location of this machine, how easy is it to access. We need to fill out some information on every piece of equipment in our plant. Part of criticality is we use the PF curve. So we can talk about design, predictive, preventative maintenance. What is the failure mode of this piece of equipment? What kind of preventative maintenance can we use to prevent failure? And how can we implement this plan? When we look at the PF curve, how it corresponds to vibration analysis, we need to look at how can we predict failures. So what kind of failures can we predict early so that we can take preventative maintenance and predictive maintenance actions such as lubrication or alignment, and what pieces of equipment fail quickly to where we're going to be more corrective actions later on in the PF curve. So what pieces of equipment need very early detection so that we can identify the faults and make changes, and which ones do not require to be identified very early on. Using that, we can decide on a very low level, such as overall meter or a walkaround analyzer, through to a wireless system, make it piezoelectric or MEMS sensors that can maybe take some more data, much more data than a walkaround system, all the way to online and a protection system. Online meaning will be identified immediately of any alarms, alerts, or protection where it actually shuts down the machine. So one size does not fit all. Not every machine requires a full online protection system to protect the plant for environmental reasons. So we need to identify what is the machine, who is the team that's implementing the information on those machines, what is the goal of the vibration program, where are we going to mount sensors or take data, and then we need to enact that plan and start acting towards a better system. We need to eliminate the phrase, well, we've always done it that way, and make some good changes to better prevent failures. So let's talk about a plan for a specific fan. So this is a baghouse fan in the packaging area of a unit. This fan may be readily available, and there may be a lot of similar fans at the facility. Its criticality, though, is very high because when it goes down, it shuts down the entire area, meaning that the loss of production, possible environmental. So the main failure modes we looked at are it's going to wear out or performance, meaning it's not acting to its abilities and slowing down the process. We decided that vibration and temperature analysis is going to be the best way to trend failures with this piece of equipment. And then we have some proactive maintenance strategies that we can use to avoid wear out and performance defects such as alignment, balancing, and lubrication so that we can do the precision maintenance and prevent these failures from actually happening. So with that in mind, let's talk about the three main options for doing vibration analysis. Those start from a portable on-demand and route-based walk-around analyzer into wireless solutions such as MEMS sensors and piezoelectric sensors, and all the way up to a continuous online wired system using piezoelectric and prox probes and other sensors. The first we're going to talk about is periodic on-demand using a portable vibration monitoring system. This is going to be your classic walk-around analyzer that everyone knows from the early days of vibration analysis. So using a periodic portable online vibration system has some definite benefits. You're going to have a trained user that controls data collection so he can adapt to varying operating conditions and speed in the field based on what he sees and analyzes while he's out there. He's going to be on site collecting data so he can visually inspect equipment while he's walking around the plant. Rugged designs, they're designed for harsh environments. Multi-channel data analysis is available on many boxes. Wireless and wired options for the walk-around are available, and they can be used in EX and intrinsically safe areas. Collecting data in person allows the analyst to really get to the root of a vibration issue. It could be on his periodic collection, or he can go out in the field with his walk-around analyzer and conduct some additional testing to verify defects. So he can run root cause analysis in the field, doing run-up coast-down testing and modal analysis for looking for natural frequencies and resonance. He can do ODS to look for structural looseness and defects. He can run cross-channel phase to diagnose things such as looseness or misalignment. And he can conduct balancing in the field if he diagnoses that unbalance is happening. So there's a lot of flexibility with running a portable system that the analyst is able to act in the field. They can also reach hard-to-reach equipment due to an environmental or a safety issue that allows the user not to be able to go right up to the equipment and put their sensor on it. They can use breakout boxes and pre-wired sensors, though there is a cost to this. So what are the cons of a walk-around portable system? So we've talked about how it's flexible and users can use it, but the collection period is typically 1 to 3 months, monthly or quarterly, based on the fact that a user actually has to go out in the field and collect this data. So there's time and labor involved in this process. So they're not able to collect data likely every day on every piece of equipment in your plant. It also requires trained personnel, so ISO certified analysts to go out and collect the data, so they're collecting data in the proper manner. There's the chances of human error because they're moving the sensor around as they walk around the facility. They could be taking data in the wrong place or on machines that aren't running, or when machines are in changing states or conditions, which can offset and throw off your data. And there's a cost because of this labor intensive. There's a human cost and a physical cost to have trained personnel and labor hours to take the data. So next we're going to talk about wireless vibration monitoring. And this can come in a lot of different shapes and forms. There's piezoelectric and MEMS sensors in this area, and really covers a lot of your balance of plant and pieces of equipment. So wireless vibration monitoring lives in the middle ground, and it's the hot topic these days, but it lives to where you need more than periodic walk-around data collection and probably less than a real-time online monitoring system. The real benefit is cutting those wires and not having all that extra installation cost, but it should not be used to replace an online system, as it's really designed to take data a few times a day and not all the time every couple of minutes. So everyone wants to go wireless. There's a cost involved with installing a wired system. There's labor, there's materials, and there's a huge cost savings and the amount of time it takes to install a wired system versus a wireless system. So there's a easy to deploy, rapid deployment, and lots of data that can be collected. So the ease of installation can really be cut in half for installing a wireless system. It takes half the time and half the amount of employees to install a 16 sensor wireless system versus a wired system. That's due to there's no cost for materials, for conduit, for wires, and the personnel cost takes a lot less when you're not pulling wires through long cable runs. There's some benefit also with the wireless. You can install them and deploy them in harsh environments where safety is a problem and you don't want to send personnel to take data, such as places where the chances of environmental releases, with confined spaces, and other hazardous areas. There's also a real functional and cost-effective reason for going to a wireless system. You can quickly deploy them at remote pumping stations, long conveyor runs, or mobile machines where wires get in the way and affect the process. It has a lower cost compared to a classic wired system. and is definitely a more proactive than a portable data collector, as you can collect a lot more data in the same amount of time. It can also take measurements where sending people might be cost inhibitive, such as those remote pumping stations, where it may take them hours to get to the site. It's also easy to add new sensors to an existing installation. So you can start with one machine, 4 sensors, get it off the ground and running, get some success, and slowly or quickly expand that to the greater plant and install more sensors. So you can think much larger scale, but start small to proof of concept. The wireless dream is data collection and transmission as fast as a wired online system and range of a mobile phone, so miles of range. And one day we may get there. But today, back to reality. There are some cons to a wireless system. So it is great for your balance of plant, your constantly running machines, your pumps and fans and things that are simpler machines. But you have to remember it's battery powered. So their batteries do die. And when they die, you have to either replace the batteries or the sensors. And a lot of installations are taking too much data, so the batteries are dying quickly, and maintenance crews are spending more time changing batteries than lubricating bearings and aligning pumps. I think a lot of these systems are also oversold and under-deliver. So they're oversold that they can solve all your problems, but really they don't work in all applications. The sensors are also sold as smart sensors with minimal smart options. So most of these sensors turn on, collect data at the interval that you've set them to collect data off, and then they go back to sleep to preserve battery. They won't trigger based on alarm, and they won't wake up if something happens, like a condition or state change. And most people are just asking too much of their systems. So they're asking for these to work on slow speed machines that require long time waveforms and acquisition times and need extensive frequency ranges. These MEMS sensors that you see on the market a lot do have limitations with them. So we need to focus on the right applications to fully benefit from wireless technologies. And that's really a lot of your balance of plant in that middle range of criticality and accessibility. So we have to remember that we're getting a lot of data on a wireless system. If you set it just to collect once a day versus your periodic walk-around data collection, you're collecting 30 to 90 times more data than just collecting once a month or once every quarter. So you have to remember who's looking at this data. Is the machine constant, running at a constant load, constant condition? So if you're feeding this data into AI or big data, is the trend going to make sense, or is it going to constantly bounce around where the trending is hard to take actionable data on? We want to make sure the data that we're collecting is data that's usable and there's someone looking at it that's going to have access to it. If we're taking data just for data's sake, then maybe there's another system that we need to look into. So when we're looking at wireless data, we want to make sure that we have a nice consistent trend with actionable data. That trend up top bounces up and down a lot. Is that just because our machine's turning on and off and we're collecting data when it's not running, or it's changing load? We also want to make sure that we have spectrums that are not changing speed so that the spectrum is easy to review data and take action on, and that we can take a long enough time waveform to analyze our data. Remember, on slow speed machines, we need to get 6 revolutions to 10 revolutions of the shaft. So if you can only take a 10 to 15 second waveform, are you getting enough revolutions of the shaft on a slow speed machine to use a wireless sensor? Or is there a better option? That better option would be an online wired vibration monitoring system. So this could use your traditional piezoelectric sensor. It could also use prox probes, temperature, thermocouples, anything that you could feed data into, and basically give the operator more actionable data so that they can make choices and decisions and analyze. So when we look back at our chart to decide, well, where do we need to use a wired system? This is typically going to be your core, critical, and complex machines. So there's 2 things that come into play with a wired online continuous monitoring system. Is it critical to the plant's reliability? So when it shuts down the whole plant. And is it complex? So does it have lots of different state changes and condition changes and speed changes that would require a smarter system to be able to collect the data? That's where we'll go from a wireless into a wired system. Now, our portable online can do a lot of these. It just takes much more man hours to where continuously monitoring it can be a cost-effective solution in the long run. So an online wired system provides tailored monitoring solutions for your critical and complex equipment. The main reasons being there's no limitations for input types. So a wireless system has two main vibration types, the MEMS and piezoelectric sensors, and then they can take surface temperatures. Whereas a wired system can take in all different types of process data, accelerometer inputs, DC inputs, tach, pulses, speed, proximity probes, you name it, it can take that data in. So we can use all that data to get a better picture on the machine health. There's also extended capacity with multiple inputs, so you can look at multiple parts of the machine simultaneously with an online monitored system. It can also take in programming languages such as Modbus, OPC UA, Profinet, you name it, we can take that in. And then real-time 24/7 monitoring. So an online system is always on, always watching, always looking at the data. So it can trigger an alarm anytime an alarm changes or a condition changes or the speed changes to take data. There's also integrated storage in some of these so that if it loses access with its gateway or its server, it saves the data and it doesn't get lost. It can also take in logical inputs and outputs, so it can send out triggers or take in triggers from the PLC. We have the option of multiple packaging for these systems. Sometimes they're just standalone, sometimes they come in pre-wired cabinets, and sometimes they're rapidly deployed and able to be moved around in mobile with some kind of case so that you can move them around inside your facility and concentrate on critical equipment as the need arises. The main difference with a wired system is typically you're going to use a piezoelectric accelerometer versus a MEMS sensor. So a piezoelectric accelerometer has a higher frequency range that the online system is able to accommodate. It has larger temperature ranges and dynamic range, so it can take larger hits, shocks, impacts, and they typically have a larger lifespan. So you can get much more detailed data than you can get out of a MEMS sensor, a wireless MEMS sensor. A lot of these sensors come in single axis, triax with temp, proximity probes. There's lots of different options that we can get out there. Sometimes size constraint is also important, but the other thing is we can attach these systems onto pre-existing protection systems or field-mounted accelerometers that you may have put in for a portable system, and we can take that data into our wired system and feed it into our database. So we can have the protection of a protection system where it shuts down the equipment, and we can also analyze the data to be proactive with our maintenance schedules and our maintenance solutions. So our monitoring capabilities with a wired online system are continuous and real-time operating or triggered by an operation state or a change in condition. We can store this data based on a periodic storage. We can store based off alarm, change of state, or change of status. So we're constantly looking at the data and getting triggered measurements anytime there's a change in the system. Most wireless systems on the market do not have that ability. So this is where if a machine fails quickly, we have the ability to act and get data on that right away. Why would we need to manage operating condition? Because a lot of machines, especially with the widespread use of VFDs, change speeds and loads constantly throughout the process, conditions, and throughout their lifetime. So an alarm setting for a high-speed machine versus a low-speed setting may be completely different settings, and you may miss alarms if you have them all set to the same thing. So they could have the same values as high speed and low speed, but they mean a very different thing when they're alarming at low speed versus high speed. There's also the ability to monitor stability control. So if the state is changing, the speed's changing, the conditions are changing in the system, we can delay the collection of data until we hit a stable state. That'll give us more accurate spectrums and waveforms and better let us trend the data so that we can feed it into our big data and our AI systems. There's also real-time monitoring. What that can do is give us event data on any kind of triggered event. So we can do postmortem analysis and deeper analysis on these failures or events that might lead to a failure by looking at, well, what led up to that failure? We can put pre-triggers because the system is looking at the data 24/7, 365, instead of waking up and triggering based on a preset periodic measurement. With an MVX or an online system, we can set a threshold and it will record before that threshold even happened, allowing us greater data, greater chance to diagnose faults. One example could be a wind turbine if we're talking about changing states and conditions. So a wind turbine has multiple speeds that they operate at and multiple power ratings that they operate at. So we don't want to trend the data from the low speed, low power rating with the high speed, high power rating where there's a higher load on the equipment. So we want to have separate sets of alarms for the low, mid, and high condition and be able to act on that data based on what's going on inside the system. So it's going to better allow the analysts to analyze that data and help our AI. Let's also talk about software. So you can have the wired, the wireless sensors, and everything can be perfect, but without a good software to analyze your data and tie it all together, it's going to be hard to run a successful program. So the software has 3 layers for most facilities. It's the management level. They need easy to digest status, action plans, KPIs, reporting. The operations level, they need alarm notifications and quick action plans so that they can stay in operation. And the analyst needs as much data as possible, speed references, historical data, process conditions, and come up with maintenance actions and plans based on the diagnosis that they put down. So we need a software to be able to have these different areas so they're not overlapping and you're not giving too much data that can confuse people, and you have enough data when you need it. Part of that is communication. So our software should be able to communicate with different systems, PLCs, SCADA, CMMS, and also be able to talk the protocols that they use. So that might be Modbus or MQTT or OPC-UA, and be able to relay all this information and make it relevant to the pieces of equipment that we're looking at. So you could have all the data you want, but if it doesn't fall into a bucket under that piece of equipment where the analyst can take action with it, it's going to be useless. So we need that data to be organized and relayed exactly when an event happens so that it can be used to better analyze that equipment. So one option for this is our Acoem Nest software with Nest Vision. We have the ability to compile wireless, wired online, walkaround portable, MEMS, and piezoelectric sensors into one platform, in addition to also using our lasers on that same platform. So we have the Nest Vision, where management and operations can get easy, quick, actionable data, and Nest Eye 4.0, where the analysts can dig in and analyze the data and get all the details that they need. The operations can also get data out of our Nest and our online systems via Modbus and OPC-UA so that operations can get quick, actionable data when things go into alarm. We really want to look at a holistic process when you're looking at vibration inside your plant. It's not one size fits all. There's a good solution for every piece of equipment in your plant, and it usually involves a combination of wireless, wired, and portable online systems. So your most critical equipment, like your critical compressor there in the middle, is probably going to require a continuous monitoring online system because it could shut down the whole plant. Whereas that fan up in the upper corner may not shut down the whole plant, but it's in a hard to reach area that the portable system can't really get to easily and effectively and puts your personnel in danger. The pumps down at the bottom, portable's a great solution. They have a full online spare. They can just switch to another pump when it fails, but you still want to know before it fails so that you can have parts ordered and it doesn't sit in a down state without a spare for too long. Let's talk about a case history to talk about where we might use portable or online or wireless systems. So this is a rotary lime kiln, a paper mill. It is a very critical piece of equipment. It only shuts down once every 16 months, and it has main trunnion bearings, which are slow-moving, high-torque applications, able to accommodate the heavy load of the lime kiln. The client was trying to develop a long-term solution. They had wireless systems on the lime kiln, and they were not getting very good actionable data because of the slow speed nature of the kiln. These bearings see about 4 RPM of revolution, and the wireless system was not able to take long enough time waveforms to get good data. However, the plant was able to collect data with their portable online system. It just took up a lot of the analyst's time. So it took a few hours for the analyst to take this lime kiln and all the associated equipment, meaning a few hours out of his day that he's in a hot, dry, dusty environment where it would be better to have an online system being placed. And it takes a long time due to the length of the time waveforms he had to collect to get good data. This was possible, though, with a portable system with the right amount of patience. Using the portable system and then installing a temporary wired online system, we were able to take 80-second waveforms and able to capture multiple revolutions of the bearing, and we're able to diagnose multiple impacting and an increase in acceleration during the time that the online system was installed. The analyst quickly identified this as a bearing defect inside the trunnion bearing. Action was identified and scheduled for the next planned outage, considering there's very long outage intervals on this machine. They were able to squeeze it in instead of waiting another 18 months to replace that bearing. The result was a bearing that was completely destroyed and slowly getting eaten away due to the defects. Let's quickly talk about some other applications and where you could use wireless, online, or portable, or a combination of the three to analyze equipment. So here's a pretty common theme: constant state blower fan, overhung fan, could be an overhung pump. You're going to see this at just about every facility out there. This can really cover all three methods. Wireless would be a great option for this, especially if it's in a hard to reach area or somewhere with environmental concerns. Because of the failure mode, online walk-around monitoring would be an excellent option as well, because taking data every month would be plenty of time to identify a failure. If you really wanted to, though, there's no reason you couldn't throw a wired online system on here if you had some neighboring equipment or if the conditions or state changes happen more often. A petrochemical plant with constant speed pump and intrinsically safe area. There's really only a few options for this. You can definitely take it with a walk-around system, especially if it's constant speed, constant load, just like in the previous state. You can get an intrinsically safe walk-around system, but you will have to put personnel in that intrinsically safe area, so they will possibly be in environmental or harm's way. There are a few wireless sensors on the market that are rated for intrinsically safe and would be an excellent option for this system because you don't have to run wires and they're in a contained environment. And an MVX may not be the best option for this, or a wired online system, because you will have to encase all the wires and put them in intrinsically safe conduit trays, and the cost expense would probably be too great. The next is a central utility plant refrigeration compressor. This is probably a better case for a portable walk-around system or an MVX. These refrigeration compressors change state and conditions rapidly if you do not have an operator there to set the conditions. So an operator could set the conditions and then go take data with their portable system and make sure they're taking data in the same state every single time they collect. Their failure mode is also relatively slow compared to other systems, so it does take a while for a failure to develop. But if you wanted to, you could use an MVX or an online system on here because it would allow for the changing state and speed of the compressor that would give you actionable trends and data. A hot rolling mill is most likely going to be an online system. They change states a lot with bars coming in and out of the mill. They change speeds based on the grade and the type of bar that they're rolling, and need a lot of inputs, process inputs, to make sure that you have actionable trends and data. A paper machine and a winder. Paper machines have been collected with portable walk-around system for years, and it can get you plenty of actionable data. They do sometimes have very quick failure modes, especially if water is involved. So online systems are a great option for a paper machine. They can adapt to the changing speeds and states based on the grades of paper that you're running, and they can take in that data. Wireless systems could be an option if your machine always runs at the same speed, but there's no trigger to say that the machine is starting and stopping, or there's a defect in the machine causing it to stop, so it'll just turn on and take data. So probably not the best application. The winder as well turns on and off based on when there's paper in the winder getting rolled. So an online system or a walk-around system is best used so that the operator can either A, decide when to take data with a walk-around system, or you use a process trigger to determine that the online system should take data. An air handler unit is an excellent place for a wireless system. They're in a confined space usually that is not able to be opened during operation due to lack of guards or process conditions. Typically run at a constant speed, sometimes on a VFD, but typically a constant speed. And the wireless can usually get to the outside of the case without drilling any holes or running any conduit. So wireless would be an excellent option for these. An automotive press pretty much only has one option. That's going to be a continuous online monitoring system. The number of changes of state and the continuous monitoring is the way to go so that you can collect data when the machine is in the same state every single time for trending and proper analysis. Cranes are another one that a wired online system is the way to go. They are constantly changing direction, speed, state, and load, and you can take all that data into your online system and you can accurately trend the data. A wireless system will have trouble with the start and stop nature of the crane and also the changing speeds and loads while it's taking data. So you will have trouble with accurate trending data. A wind turbine, another great for a wired online system. As we talked about earlier, you can accurately take in load and speed data so that you can put proper alarming and trends and feed that data into your CMS system. In summary, there's a few things that you need for a successful program. Survey your facility and make a plan to implement your program. So that involves looking at your equipment and determining its criticality and its changing states and its layout. Implement your wireless and wired vibration system as it was designed. Don't ask a wireless sensor to do what an online system is designed to do, such as shutdowns or constantly taking data that would require rapid battery replacement and changes. And start with your critical and low-hanging fruit and build on your success. So the key is correctly identify and diagnose equipment that's low-hanging fruit and document and build on that success to grow your program throughout the facility. If you don't document your success, it's hard to build a culture of a successful reliability program, especially with vibration analysis. So document your wins and grow your program to implement more pieces of equipment in your plant. Thank you for joining us with our webinar today. I'm Eyman with Acoem.